truism that everyone can't be everywhere at the same time applies particularly to atomic tests. It is impossible for all of us to be on hand at the test site, or all of us to ride in the drop plane, or for any of us to be at ground zero at H hour. But there is a way to solve this problem, and that is with photography. A camera can take us into the very interior of a nuclear weapon as the weaponeer makes final preparations for detonation. It shows us ground zero as it appears from 25,000 feet on the final bomb run. It slows down the split-second birth of a nuclear blast so that we can apply a tape measure to it. Photography, in a sense, allows everyone to be everywhere at the same time. And on atomic test projects, such as Operation Tumbler, for example, photography serves a number of important functions. For documentary use, a film story explains the overall aspects and objectives of the test. For technical purposes, a step-by-step film is made of technical procedure, such as installing complicated instruments. For scientific study, special equipment, such as high-speed cameras, record nuclear phenomena for analysis by scientific investigators. While all functions of photography are important, our concern is with scientific photography, particularly the results of remotely operated cameras in relation to Operation Tumbler conducted in Nevada in the spring of 1952. Our problem was to study the velocity and form of blast and the character of thermal effects. This study was of great importance since in previous tests, some nuclear weapons had produced substantially less than the expected blast pressure. What was happening to lessen the full effect of the blast? Where and why were our estimated blast curves so much in error? One factor in lessening the full effect of blast could be the shock-reflecting characteristics of the target. Another could be the thermal radiation, which might cause the dust on the ground to stir up to such an extent that it cushions the shock wave. It might heat up the ground and the air layer close to the ground to such a degree that it would alter or soften the full effect of the blast or the development of the total potential force of the reflected pressure wave. On the other hand, perhaps there is a completely unknown reason for the variation in blast results. To investigate these possibilities, we set up an outdoor scientific laboratory at Ground Zero. Instruments, gauges, cameras, and other test equipment are all installed according to plan. To orient us for the pattern of action, let's study this model map of the test site at Ground Zero. To the right of Ground Zero is the white rocket line used in the study of shock velocity. The brown rocket line close by is for particle velocity measurement. Camera stations in trucks are directed toward these two rocket lines. Motion of the air mass can be studied in JATO plumes and smoke puffs set 500 feet from the blast line towers. These JATO plumes and smoke puffs are filmed from camera stations here indicated by arrows. Photography for the study of thermal effects is obtained from pillbox camera stations about 3 feet high and in a row displaced 200 feet from the blast line towers. These towers extend more than 2 miles from Ground Zero. From these cameras and others mounted above the dust, it is possible to get a record of thermal effects at varying distances from the blast. Now, at the test site, the instrumentation is complete. Everything is in readiness, personnel removed, Ground Zero deserted, waiting. High above, at 25,000 feet, the drop plane is in its final bomb run. A camera in the bomb bay records the fall of the weapon. Bombs away. To study the velocity of shock propagation from the blast, a row of smoke rockets is shot into the air 3,000 feet from ground zero. Using this, the progress of the shock wave can be calculated as a function of distance. From the shock velocity in turn, it is possible to calculate overpressure without the disturbance introduced by ordinary pressure gauges. The arrow in the next scene indicates the falling bomb. Before we analyze this burst, let's return to our model map for a moment. The camera position for this phase of the test is on the opposite side of the burst from the trails and 3 miles from ground zero. The smoke trails themselves do not move, but the camera records the distortion in their images produced by refraction as the edge of the shock wave progresses in space. This distortion, in the form of refracted hooks, can be measured and analyzed best when the smoke grid is in a plane perpendicular to the optical axis. Now let's analyze the burst, as recorded by a high-speed camera at 2,400 frames per second. Refraction hooks will appear on the 3 trails to the left, an arrow indicating the first appearance on each trail. Now let's repeat the action at a faster speed. Refraction hooks again appear on the trail, while the phenomenon known as the Wilson cloud chamber forms beneath the fireball. The cloud chamber is formed by the rapid condensation of moisture in the rarefied air. For the measurement of particle velocity, rockets are fired in a row extending radially from ground zero, as indicated on the model by brown smoke trails. The camera position here is 2 7/10 miles away and at right angles to the smoke trails. This is an approximate view from the camera toward the smoke trails. The white or hook trails are visible in the background. In this technique, a particle of smoke is considered the same as a particle of air, and the actual motion of a particle caused by a shock wave is visible and can be measured. In the next scene of live photography, you will see the front of the shock wave bowing the smoke trails. In the background, refracted hooks are visible. An arrow indicates the trajectory of the triple point, as manifested by the shears in the trails and in the lower surface of the cloud chamber. Since the triple point, or Mach stem, is an important factor in blast pressure, let's examine an atomic detonation, which diagrammatically looks like this. 4 effects are produced: light, heat, radiation, and blast, or air pressure. Our study in this instance is concerned with blast. The pressure wave produced by the energy released from the bomb moves in all directions at the same time. This approaches the Earth in what is known as an incident shock wave. The air is heated by the sudden compression caused by the shock wave. As the incident wave strikes the ground, most of the energy bounces back in a reflected wave. The resultant peak pressure at the point of reflection is considerably greater than the pressure in the incident wave, thereby increasing the destructive force of the shock force, or front, moving across the ground. Because the air behind the incident wave is hot, the reflected wave can move faster and gradually raise the base portion of the incident wave into a wall or stem of boosted air pressure, called the Mach stem. On a graph, the event looks like this. The greatest pressure, of course, is produced at ground zero by the combination of the incident and reflected waves. The pressure gradually drops off as the wave moves out from ground zero until the Mach Y develops and increases the pressure again. Now let's repeat the scene of the actual burst to observe the bowing of the particle trails, the movement of the refracted hooks, and the Mach-wise stem. Note also how the shock wave moves the JATO columns and puff of smoke in the foreground. Now let's take a look at the same scene from further away. The next phase in the study of shock front is concerned with the motion of air mass wherein air is labeled by smoke. This experiment, conceived by LASL, illustrates the shape of the shock front as it deflects columns of smoke emitted from inverted JATOs to a height of 200 feet and mortar shell smoke puffs 200 to 300 feet high. There's the burst. Watch the reflected wave bounce back up and hit the fireball. The shock moves both JATO columns and smoke puffs. Both the positive and negative phases of the shock are indicated by the to and fro movement of the smoke. Here about 2,000 feet from ground zero. Since this action occurred in a split second, let's repeat the scene. In the study of motion of the air mass, smoke particles are identical to air particles, and by photographing their motion from these various camera positions indicated on the model, we can measure the air molecular velocities and hence compute temperature and pressure. JATO columns, smoke puffs, and particle velocity trails are new techniques in this test. In the next series of scenes, taken by high-speed cameras at 400 frames per second, the fronts of the incident and reflected waves will be seen by refraction against smoke trails, and also by motion of smoke puffs within a graticule. Watch the arrow pointing to the shock wave as it moves from right to left. This is 1,500 feet from zero. We catch the same wave at 3,000 feet from zero. Watch the puffs move. The white dots streaking at the left side are timing marks. Now at 3,750 feet from zero, we see it again. At 4,500 feet from zero, the V formed by the two waves is considerably narrower. At 5,250 feet, we see the effect of the wave on the puffs and the JATO smoke column. At 7,500 feet, the wave is almost invisible, but its effect is still clearly apparent. Now the same wave at normal speed, 3,000 feet from zero, to show the rapidity with which the events actually take place. Now we see a precursor wave. Note that it precedes the incident wave, which shows its effect on the puffs, and the reflected wave, which is visible. This scene also shows the cloud chamber forming and then disappearing. Of particular interest in this next scene is the effect of the shock front on the JATO plume, especially the shearing pressure of the triple point or Mach-wise stem. The path of the latter is clearly indicated by the sharp line at the bottom of the cloud chamber. Thermal effects photography was undertaken by AFSWAP to supplement their general blast measurement program. The study is to indicate the presence or absence of thermal dust caused by the bomb's thermal pulse, and to correlate this with readings of blast gauges. The cameras are enclosed in pillboxes on a line with the blast line towers. Smoke generators produce visible particles that show the flow of the air pre-zero, whether it is laminar or turbulent. Photography of this will also give a qualitative estimate of velocity. Here we see the blast tower at predicted ground zero from a camera in a pillbox 200 feet away. The post-zero footage at 1.5 times normal speed shows the event occurring in less than a second. And now the same scene with each frame held for half a second. The lights visible in this scene are for studying absorption characteristics of the dust. This action is also shown with each frame held for half a second. The blast tower appearing is 1,500 feet from ground zero. This is a view from a camera raised above the dust level on a 17-foot pole. The blast station visible is 2,000 feet from zero. In this scene, lights were placed on a pole with the top light 12 feet above the ground. No pre-shock arrival of dust is observed at this station, 3,000 feet from zero. The top dust transmission light shows effectively. This is the same station viewed from the 17-foot pole. Here we view the blast tower at ground zero again, at 48 frames per second from 200 feet. This is also printed holding each frame for half a second. The arrow now shows our new angle of view for the next scene, taken with a high-speed camera at 310 frames per second from a tower 750 feet from zero. Particularly, note the shock front. In this scene, the four lights were placed close to the ground in an attempt to measure transient gradient above the ground by mirage effect. And again, with each frame held for half a second. This blast station is 1,500 feet from ground zero. Our next blast station is 3,000 feet from zero, and the action is filmed at 36 frames per second. Then repeated, slower. The arrow in the model now shows a camera position 3,000 feet from zero and aimed into the sagebrush away from the blast line. The objective here is to determine the difference between thermal dust in this area and dust along the blast line. Now, back along the blast line, this scene of a tower 4,500 feet from zero is filmed at 48 frames per second. At the same camera speed, this view is of a tower 6,000 feet from zero. This scene is of a tower 9,000 feet from zero. Our angle of view is now changed to the position indicated by the arrow. The camera is on a pole 9,000 feet from zero and looks straight down the blast line. Mortar puffs and particle trails are included in this scene of thermal dust. Thus, blast and thermal phenomena on Operation Tumbler have been recorded by high-speed photography for analysis and evaluation by various technical and scientific authorities. It is obvious that the results obtained by such special equipment are sure to suggest further avenues of research and experimentation in the program of increasing understanding of nuclear phenomena.